In this video, we will compute how the boiling point of water depends on the elevation above sea level. Roughly, it's -1 degree Celsius per 1,000 feet above sea level. Therefore, at an elevation of 1,000 feet, the boiling point of water is 99 degrees Celsius. At an elevation of 10,000 feet, the boiling point of water is 90 degrees Celsius. So first, let's look at the Boltzmann distribution. It tells us the air density or pressure is proportional to this exponential function. M is the average mass of the air molecule. G is the gravitational acceleration. H is the elevation, and Kb is the Boltzmann constant. T is the temperature. From this, we can get the ratio of pressures to be this equation. And then we take the natural logarithm of both sides. And then we have the natural logarithm of the ratio of pressures to be -mg, the difference between the elevations divided by kBt. The Clausius-Clapeyron equation we learned in physical chemistry tells us the natural logarithm of the ratio of vapor pressure of the liquid is equal to negative enthalpy of vaporization over R times 1 over Tb under this external pressure P2 minus 1 over Tb, the boiling point under external pressure P1. So if we look at these two equations, they share the same left-hand side. Therefore, we can equate this part with this part, and then we have this equation. And then we can replace H1 with 0, which is the zero reference or the sea level, and then the boiling point at sea level is 373 Kelvin, and then we just plug in these two numbers, and then we can just replace H2 with H, Tb2 with Tb. We get this simpler equation here. And if we multiply both sides by R, this R disappears, and R over Kb is the Avogadro constant. The Avogadro constant times the mass of one average air molecule is the molar mass of the average air molecules. And this uppercase M is roughly 0.029 kilogram per mole. This is the weighted average of oxygen and nitrogen. And then we're going to use this 295 K as the temperature of the air. And then we plug in some other numbers. The enthalpy of vaporization of water is roughly 41 kilojoule per mole, and the gravitational acceleration is roughly 9.8. And then H, we're going to convert it to from meter to feet, and it's going to be 0.3048 meter per foot. And then we plug in all other numbers, we'll get a result here. The temperature decrease is approximately the elevation divided by 1,000 feet. The unit is Kelvin or degrees Celsius. Remember, if we're talking about the temperature change, these two units are exactly the same. A temperature change of 1 Kelvin is exactly the same as the temperature change of 1 degree Celsius. Okay, the conclusion is very simple. So if you want to know the boiling point of water on top of Mt Rainier, you simply just look up its elevation and then divide that elevation by 1,000 feet. You get a number, and then use 100 degrees Celsius minus the number you just got. You get the boiling point of water on top of Mt Rainier. Now let's look at 3 numerical examples. First, Ellensburg. The elevation of Ellensburg is roughly 1,500 feet. So our predicted boiling point of water is this guy divided by 1,000. You get 1.5, and then 100 degrees Celsius minus 1.5, and 98.5 is our prediction. Experimentally, we measured the boiling point of water. In Ellensburg, it's roughly 98.6. Now how about Mount Rainier? On top of Mount Rainier, the boiling point of water is 100 minus 14.4, so our prediction is 85.6. Roughly it's 85 degrees Celsius. How about Mount Everest? The elevation is 29,000 feet, and then the boiling point is 100 minus 29, so our prediction is 71. And well, indeed, the boiling point of water on top of Mount Everest is roughly 71 degrees Celsius. And I want to show you the Ellensburg numerical example was done on wolframalpha.com. So you just simply copy paste this to your web browser, or you simply do control click, and you will see this website right here. And this is the equation I typed, and the Wolfram Alpha website will do the computation for you, and the result is 98.5 degrees Celsius over here.